Hello everybody, welcome back to another session in Python for Natural Language Processing. In the last video, we have seen how to manipulate text by using certain functions from regular expressions module. In this video, we are going to look at again text manipulation, but we will see how to use a stemming approach and then also using Porter algorithm. Stemming is a process where we remove suffixes from words to arrive at roots. Stemming can be imagined as a model of how speakers break words up into meaningful units. It can also be imagined as a practical tool so that we can find words that are morphologically related. Right? When we say a model of how speakers break up words into meaningful units, we are talking about people, linguistics, or human beings. When we are talking about a practical tool, that we are talking about in computational linguistics, where we use stemming as a tool to remove suffixes from words. Porter algorithm. In Porter algorithm, there are blocks of rules and suffixes are removed from words using these rule blocks. How are they used? In the first block, one set of rule suffixes is removed. In the next block, a different set of suffixes is removed, and so on. So that is, each block removes a particular set of suffixes. And each block consists of a set of rules which are organized disjunctively. Each rule in the block generally removes or rewrites one suffix. If more than one rule is present in a block, then the most specific rule applies and the others do not. Let's take an example here. You have a word ending SSES or word ending IES, words ending SS and words ending S. So SSES is mapped to SS. That means ES is removed. From IES, I is removed. If it is SS, only SS is removed. SS appears. If there is only single S, that becomes null. Right? This is a block of rules. Now this block of rules will map the word caresses to caress, carries to carry, looks to look, because there is only S, so removed. Note that the disjunctive requirement entails that caresses is not mapped to caress. That is, it doesn't apply, the fourth rule will not apply, or the third rule does not apply, or the second rule does not apply. Only the first rule applies. Right? That's why what we are saying is these rules are disjunctive in nature. Right? Rules are subject to conditions. So in addition to rules in the Porter algorithm, what we have is conditions. Each rule is subject to a condition. Most often this is a condition on the size of the stem. Once you remove the suffix, whatever remains is a stem, and based on the length of the stem, the condition applies. So, but it can include other information as well. For example, whether the final consonant is doubled or the identity of the final consonant, and so on, depending on last consonant usually. How do we implement this algorithm? The first step to implement is to code up Porter's measure function. Measure function is very important in Porter's algorithm. Many of Porter's rules depend on the size of the remaining stem when some putative suffix is removed. Once the suffix is removed, there is a stem. What is the size of the stem? What is the length? So the measure of a stem is defined in terms of consonant and vowels. How do we measure the stem? We measure it in terms of consonants and vowels. How many vowels are there? How many consonants are there? What follows what? Right? That is important. So specifically, a consonant is defined as a letter other than A, E, I, O, U or Y. Y is also considered a kind of vowel here. In the case of Y, it is a consonant if it is not preceded by a consonant. So Y is a consonant if it is not preceded by a consonant. Like for example, when you say try, Y is preceded by R, so it is a consonant. We therefore start with a function to determine whether some specific letter in a string is a consonant. Right? So what we saw is here is If Y is preceded by a consonant, it is a consonant. If it is preceded by a vowel like A, for example, you have the word like stay, S-T-A-Y, then Y is a vowel, right? So if you take C to be a consonant and V to be a vowel, then this is the regular expression which Potter uses. C asterisk V plus C plus again asterisk V asterisk, right? So this is the regular expression which is used. That means basically V and C are important. How many times VC appears in the stem. So the measure of a stem is defined as the number of times the VC or V plus C plus part matches. In simple words, it is a measure of a string is the number of times the sequence VC occurs. How many times VC sequence occur in a stem? Based on that, you have the measure. So measure is 0 if you do not have any VC, right? Any VC sequence. So in TR there is no VC sequence, EE there is no VC sequence, TRE also there is no, there is a CV sequence here, not VC. Remember, M is equal to 1 if there is one VC sequence. Where is the VC sequence? UB. Here AT, here ES, here IV. M equal to 2 if there are two VC sequences. What are the two VC sequences here? UB and ES. Here IV and AT. Here AT and EN. Here OR and ER. Right? So that's what he means by measure. Right? Measure is very important in implementation of the Potter's algorithm. Now rules. We said Potter algorithm has rules. That is, there are blocks of rules. And how is each rule? Now let's look at that. Potter's rules have three main components. What are the three main components? There is a test to see if the form ends in some particular ending string of letters. It first looks at whether that string has a particular ending. Second, there are other tests on the remainder that precedes that ending string. If those tests are true, then the ending is mapped to a different ending. Right? There are three things. One is to see whether a particular string appears. Then to see whether that string is preceded by something in the remainder. And also that if that is found, then that ending is changed to a different reading. For example, you have here M greater than 1. That is, what is M? We have seen here M for measure. M for measure. So measure is greater than 1. That means there is at least one VC sequence, and the suffix is ement, E-M-E-N-T. Then it becomes null. So here we first ask if the word ends in the string ement. If the word ends in ement, look at the stem whether it has at least one VC. If it is there, then it becomes null. Right. Second, we ask if the measure of the remaining material is greater than 1. If both of these hold, we map ement to null. Right. For example, if you look at a word like cement, C-E-M-E-N-T, you have E-M-E-N-T ending, but there is no, M is not greater than 1, M is 0. So cement remains as cement. If you look at entertainment, the word entertainment, then there is ement. And look at the stem, entertain. You have VC sequences, entertain, you have EN, ER, enter, IN again, 3. There are the M is more than 1 there, right? Because M is more than 1, that is measure is more than 1, then that remains as it is, that is it becomes 0 and entertainment. The conditions. In addition to rules, there are conditions. Potter's conditions include things like the following. Like the stem ends in S, or the stem contains a vowel in between. or the stem has double consonant, D capital double consonant, T, T, S, S, etc. Or the stem ends in CVC. O represents CVC, where the C is not W, X or Y. That means it cannot be will or hop. Okay. So the conditions on a rule, these are the conditions. Now we need to change this condition into regular expressions. Okay. That's what we are going to do when we look at the program, actual program. So the conditions on a rule can be more complex. Multiple separate conditions joined together with AND or OR. For example, you have M is greater than 1 and there's an S, or there is a T at the end of the word. The stem either ends with a S or the stem ends with a T. Look at this. The condition is M is greater than 1, right? And one of these. So the conditions or rules are always combined using either the conjunction or disjunction. Potter's algorithm has blocks, right? That's what we said in the beginning. How do they apply? The blocks are like step 1, step 2, step 3, step 4, step 5. These are all blocks, and step 1 has 3 blocks and step 5 has 2 blocks. So this applies, and this feeds into step 2. This tip feeds into this, it feeds into this feeds into this, right? So there are 8 steps which Potter defines for morphological analysis of English. Okay, we will look at this in the Jupyter notebook, how we can program using Potter's algorithm. Look at this, is the basic program which we would like to have. That is, within this we are going to build all the other modules, all the functions, etc. So you import sys, you don't need actually, we are importing sys. Define stem W, that means we are defining a stemming function. Return the W. If you want any conditions or anything else which will have between these two. Okay, word, if the word is talked, then root equal to stem of that word, that means you get the stem, and print the word which is root with a separator, right? So when we run this, we say talk gets the talked. Talked is talked because we haven't done any stemming here. Let's now remove the ed from talk. From the word talked, earlier we have seen that talked is printed as talked, but we are trying to look at remove ed suffix from talked. How do you do that? So import and sys definition of the stem function. You are taking M equal to regular expression RE module with search, and then we are searching for ed ending in the word, right? If M, then return M group. Remember group function which we have seen in the last video, right? It prints everything after the suffix is removed, group, and else return W. That means if you do not find ed, then you are getting W as returned. So word talked, root stem word, you stemming it, and print word root and separator. When you say stem word, it refers to this function, right? What does this function do? It searches for the ed and removes that. Okay, now let's run this program. Look at this, the word talked is changed to talk. So if I remove, instead of using talked, I say walked, then I get walk. Okay, if there is no end, if there is no ed ending, then walk remains as walk. Okay, so walked, we have stripped off the ed suffix and we get the stem as walk. What we have understood in Potter's algorithm is that the stem has to be converted into C's and V's so that we know the measure. Based on the stem length, the Potter algorithm. We have seen that in Porter algorithm, measure is very important. To get the measure of the stem, we need to convert the stem into consonants and vowels so that we know how many sequences of VC occur. Right? For that, we need a program to convert a stem into C's and V's. That's what we are doing in this program. Importing the modules, then we are defining a consonant. How are we defining a consonant? We take two variables. One is the letter and then other will be a index value. So letter SI, then if letter in AIOU, that is, if it's in a vowel, then it should return false because we are looking at a consonant function. Similarly, we are going to look at if the Y is a consonant or a letter. Defining vowel Y as a defining Y as a consonant or a vowel depends on what precedes and what follows it. Right? That's why it is taken I. If I equal to 0, then it becomes true. Then that is Y is taken care of as a consonant. If Y is if Y occurs and I minus 1 is a consonant, then it becomes false. So else, otherwise it's true. If these three conditions fail, then the letter is a consonant. Then we are defining stem. Stem W, return W, right? Then word is encourage. Let's take the word encourage. Print word, right? We are trying to print the word. That is encourage. For I in range length of the word, right? The word's length we'll take. So how many letters are there in this? We take that. And in that range I, for each I, what we're doing is consonant word I. That means first 0, so word 0 as a consonant. Now in the word encourage E. So it says now consonant letter here I. If letter in AIOU, so E is in AIOU, so that becomes false. So then we take the next consonant 1. So consonant 1. Consonant, then you have the letter N and I. And again it looks for that. Then it says N is not a vowel, it is a consonant. So we get, when it is consonant, it prints C. If it is not a consonant, it prints V. So you get CV structure for the word encourage now. Whatever word you give, you get CV structure. Right? This program converts your stem into C's and V's. Let's look at the output of this program. See, encourage is converted to VC, right? So if you change the word to something else like entertainment, then you get, right, you get again that structure. And this is useful now because now we have to count VCs. How many VCs are there in this word? For that we need to write another program. Now let's look at this program. This program converts the stem into C's and V's as we have seen in the earlier program, and then it also returns the number of times the sequence VC occurs in that stem. Look at this. We are importing the modules, then we are defining the consonant. Whatever we have done earlier in the program, here the same thing is written here. Then after conversion, we are defining CVW. That means we are trying to look at CV structure. Result is empty now. For I in range length of the word W, if consonant W and I, then this becomes result plus the C. That means you are adding C there. Then else you write vowel. So if it is a consonant, you write C. If it is a vowel, you write V. Return res. So it returns the measure of a string now. Define measure W. CV word is CVW. That is here, right? This function. VCS equal to find all VC CV word. So once the CV in the CV word we have all the C's and V's, then we are trying to find out all VC combination sequences. Return length of VCS. That means how many VCS are there now. So stem W, return W. Word is encouragement. Print word, print CV word, that means all the CVs and Vs, and then print the measure of a C's and V's, VC's sequences. Look at this. Encouragement is the word and it has this structure, and how many VCs are there. You can see one VC here, there is a VC here, then there is another here, another here. Total 5 VCs are there. So now, as per Potter's algorithm, we are able to convert the stem into VC structure. Then we are able to count the number of times the sequence VC occurs in the stem. Now we will see general code for handling conditions. The conditions which we have seen earlier in the slides, that we are going to look at how those conditions can be built in. You're importing and you are defining the consonant, whether it's a consonant. We have already done this. We are also changed into CV structures, and then the measure is taken care of. Then we are writing a rule now. Rule C, we are defining rule function. Rule CERW. C is a condition, S and E is the suffix, R is the replacement suffix, replacement, that is if the suffix can be replaced with something, that comes here. Then W is the word. So in the word we are looking at for a particular condition, and then the suffix, and then the suffix will be replaced with another. Right. M equal to research. That means you find if the word has E ending. Then if M, then S equal to M group 1. That means you are taking the stem there. If CS, right, C of S, that S is the stem, whatever we have there, right? CS, then return S plus R. R is the suffix which is added. So you are taking the stem, and with the stem you are adding the replacement, right? So what this function does is, what this rule does is, it finds, it takes a word, looks for the condition, and then removes the suffix, and the suffix is replaced with another suffix, right? Okay, return none. If nothing happens, if these are not met, if the condition isn't met, or if no suffix is replaced, then it returns none. Now we will define M1 condition. Conditions: M is greater than 0. If measure of X is greater than 0, return true, or return false. Then define ed rule. Right, what does ed rule do? It uses the rule which we have given earlier. So X equal to rule M1 condition, right? M1 condition which we have defined here, and then ed is the suffix, and then replace that with empty, and then W is the word. So in the word, you look for this condition, M1 condition. The condition is measure is greater than 0. Then you take the look at the suffix and replace that with empty. Return X. We are defining stem now. W is a stem. When we replace that ed with s, that means ed is removed, right? Ed is removed. What remains is a stem. That's what this rule defines. If res, return res. That is, if res is true, then return res, return W. Let's take the word talked, then print word, print stem word. Now what we see is talked is a word with ed ending, so we expect ed to be removed and print only talk. And talk, if you look at talk, how many vowels and how many consonants in the stem? We'll see C, V, C, 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 V, C, C, and there is a VC here, that is measure X is greater than 0. So ed is replaced with space, right, with empty thing. So talked becomes talk, right? Talk becomes talked. Okay, suppose we use another word, no, something like walked is also similar, so you get the same result. What the stem has to be done, whether stem has to be retained as such or stem needs some more suffix. Right, now this part of it, which is a very general code, will turn that into a module and then use it in another program. So what we have done now is this general code which we have written earlier, all that we have saved it as manip12, manipulation 12 as a module, and then we are importing that module into this program now. So whatever we have done earlier, that will be done by manip12, which is a module. We are calling that module. So import resys and manip12, and the condition we are defining here is m1 condition x. If manip12 dot measure x is greater than 0, that in manip12 we have defined measure, right? So we are using that function now. manip12 dot measure x is greater than 0, return true, otherwise return false. Then we have also defined head rule there. So that we are going to use now. Define head rule w x equal to manip12 dot rule m1 condition ed space and w, so return x. Then another is define stem w. Stem w uses head rule, which is here. So head rule w, if result is true, return result, otherwise return w. So word talked and print word stem word. In this program, what we are doing is we are importing the module which we have defined and name it as manip12. Now let's run this program. Talked becomes talk, right? Now it has done. We don't have all the program which we have written earlier now. Where is it? It's all there in manip12. Okay, if we have a word without talk, what will it give? It will give talk as talk. That means it hasn't found ed, so it hasn't met the condition, right? If it hasn't met the condition, so it give the result as it is. That's what we said, right? Return w if that condition is not met. So talk becomes talk. Till now what we have done is we have taken a word, we have looked at whether it meets a particular condition, like whether it ends in ed or not. If it ends, then we remove the suffix, and we looked at the stem. That stem is converted into CV structure. Then we looked at how many sequence of VC occurred, that we took as a measure. Depending on the measure, we wanted to convert the stem into a particular word. Right, now we have already seen in the slides there are a particular set of rules, that is SSES will be changed to SS, S can be changed to 0, etc. That is one block of rules. Now we are going to use that block of rules and define the program. This is actually following our Potter algorithm. Import regular expression sys module, and then we are also importing manip12, which we have already done. We are importing everything from there, and we are defining the first condition. Condition is if it is if measure x is greater than 0, return true, otherwise return false. Then we also have a null conditional, that is, it's a vacuous condition. If nothing applies, then this can apply, and it can give us the result. Then these are the first set of rules, first block of rules. Remember, SSES changes to SS, IS changes to 1, SS changes to S, and S to null. So if the rule, in the rule null condition, right, what is the null condition? Null condition X, it remains as it is. So change SSES to SS, then IS to I, SS to S, S to I. So these are 4 different rules now, and they are all disjunct. Only one of them applies at a time. Okay, the specific rule applies and you get the result. So this is one step 1a. If you have another block of rules, that will be step B. If you have a third set of rules, you have step C. So step 2, another set of rules. Step 3, step 4, step 5A, 5B. So you have several rules, several blocks of rules. And when all the rules are defined, then you define your stem depending on each block. Right? If it is S1A, S1A is a block here. If S1A is equal to step 1A W, S1B is step 1B S1A. So look at this, S1C is step 1C S1B. Look at whatever the result here, that is taken as the argument. Okay, it goes on like that. So that means they are working when in disjunct. That means you are using this approach to get the right result. So this is what we call stemming with blocks, and this is Potter's algorithm basically, along with the rules. So you take the word possesses and it should print the word and then the stem of the word, that is, it has to get, you have to get possess. Right? Let's run the program. Look at this, the word is possess and you get possess. So let's change the word to your first block of rules. Right, your first block of rules say that if there is only one SS, it changes to SS. Right, so if I say POSSESS, right, what does this give? Right, it gives SS. Okay, if it is another word like Mrs., what should it give? Right, are we getting the right thing? Yes. Right, Mrs. becomes Miss. Right, so this block of rules is applying for Mrs. And possesses, this rule is applied. You can get this, you can also apply this rule. For example, if you say IES ending tries, you get TRI. See, IES has changed to I. Okay, you can change, if you change this to Y, then you get your result as Y. Okay, right, then SS ending SS only, S, if there is only one single S, then it is empty. So if you have a word like days, right, S is removed and day comes. See, empty, S is removed. So this set of rules now applies very specifically, though this is a block, right, they apply very specifically, they are all disjoint. Right, now this is how the Potter algorithm works. I have given you one set of rules, that is one block of rules. In fact, in your book you have, for all the blocks are defined. What I would like you to do is open your book and look at each block of rules, define them and use the program, and also test the program. See you in the next video.